Awesome. Thank you.
Of course.
And I think it's 4, so feel free to get started.
Yeah, start whenever you'd like.
Okay, awesome. Let me just share my screen. Do you guys see the presented version? Awesome. Okay. Hi, everyone. We are UC Berkeley STAR, or UC Berkeley Space Technologies and Rocketry team. And we're super excited to kind of get to know you guys today and teach you all a little bit about what we do. So we work on a lot of high-powered rockets. As you can see over here, this is an old photo of us when everything was like in person and we were able to launch. But yeah, we participate in international and national competitions, and we really just all are here because we have a huge passion for rocketry. And I know you guys are the physics club, and I'm actually a physics major, and physics ties really, really strongly into rocketry. And hopefully we can convince you guys to be future rocket scientists today. So one of the main competitions we go to is the ESRA, Intercollegiate Rocket Engineering Competition, or Irec for short. And basically we work all year on a bunch of components of this rocket, including like payload, an airframe. We work on the propulsion. We work on a lot of different elements of this rocket. And we launch it Truth and Consequences, New Mexico, every single year. And I think last year we got 17th, if I'm not mistaken. And yeah, it's a really important competition for us. And also another element of our club is we do a lot of research. So a huge current research project right now is our liquid propulsion engines. We have some experimental liquid propulsion engines that run, and most of our rockets right now that are in competition run on solid motors. We're going to actually be going over the difference between solid motors and liquid engines today, and kind of a little bit more about how that like propulsion side of it works. And we also have had research projects that work on custom flight computers and custom tubing, as well as other components of our rocket, to kind of help us be better scientists and engineers as well. And our last kind of major component of our team is the outreach end of things, which is why we are here today. We are super, super passionate about reaching out to our local community and local high school students to really give them and spread our joy of rocketry, and hopefully inspire a lot more students to get into the field of like aerospace engineering and rocketry in general. There are a lot of components and a lot of different ways people can get involved. So yeah, stay tuned for our presentation. So I wanted to start off with a little video of our Irec launch last year, which is pretty cool. You'll kind of see what the launch process kind of looks like, and you'll kind of be seated with a front row view of our rocket. And yeah, let me just click play. Let me know if you guys can hear this.
If there's sound, we cannot hear it.
Need to share audio as a setting.
Let me know if you guys can hear it now. I should be able to.
We still cannot hear it. Oh, now we can hear it.
Oh, no,
Sounds good. So obviously this is the countdown before our rocket launches. So this first component of the flight is where most of our thrust happens because we're trying to get it off the ground and as high as we can. This is our drogue chute. And you can see our recovery team being very, very happy about this because one of the biggest parts of, or one of the most stressful parts of our rocket is having that chute release. So it comes down safely. And that's our main chute. And that thing you see swinging there is our payload. And it landed safely. So yeah. And you can see kind of like the specs of our rocket over here in terms of like altitude and feet, speed and time and all that. Or like you should be looking at the apogee as what I meant. But yeah, this was our launch last year. Moving on to some of the actual kind of fundamentals of the science behind this, I think Dylan will lead this slide.
Yep. So basically, propulsion just comes down to pumping gas out the back of it. It's fundamentally, in terms of the physics, it's not terribly complicated. It's basically momentum transfer. If you can push the gases out the back, you can impart the momentum onto the actual body of the rocket and move it up. That's why we actually have the fuels, because fuel and oxides, when they combust, release a lot of gases, and we can harness those gases and direct them downward, so we can actually make that momentum transfer happen. Solid fuel is basically when the fuel and oxides are bound together with some binding agent. It's in one solid grain and it just burns end to end. You can't really control it. It's just going. And then liquid fuel, you have much more control over it. You can throttle it. You can change the ratios it's actually combusting in. That will also usually need some external energy input to actually make the combustion begin. Then it'll be self-sustaining. But ultimately, all propulsion comes down to is make these gases, control them, make it as efficient as you can, and direct them out the back so you can make the momentum go up. If you go next slide. So in order to do this, the rocket engine has pretty much all rocket engines, regardless of the design, is going to have some common elements. First off, you're always going to have a fuel and oxidizer. This is set up for a liquid engine, where the fuel and oxides are actually stored separately. Again, if it's a solid grain, they'd be bound together into one specific motor component. The pumps, this is just another mechanism of actually moving the fuel and oxidizer down to the combustion chamber. There's also pressure fed systems, which is what we're trying to do in our liquid engine development. And again, or solids where that isn't necessary at all. The combustion chamber is where that actually happens. You combine the fuel and oxidizer into the combustion chamber. It can combust in there and then direct it downward. The nozzle is what does that direction. The nozzle is also converging and diverging, which means it will accelerate the gases that you create out, because momentum is directly proportional to velocity. So if you can accelerate it, you're going to get more momentum out of it. And one thing not depicted here is for specifically liquid engines, at the top of the combustion chamber, there's an injector that actually handles combining the fuel and oxidizer together, so you can actually make the combustion happen. So again, rocket engines, they can be big and complicated, but at the end of the day, it's just make some gases and get some momentum transfer and try to move up.
Yeah, and so another really like key component of successful rocket flight, and this is quite like a different physics concept what Dylan is talking about, but we're going to talk a little bit about stability, and then a little bit more about like the center of mass and center of pressure of a rocket and what that has to do with having like a stable and really nice flight. And so there's kind of like three methods of achieving stability in flight, but just for context, stability, it's pretty intuitive, but I think most people don't realize that stability is kind of about finding a balance between having a rocket that's able to be really stable in flight and then also not get too affected by things like wind conditions and random motion that can happen during a launch that could like severely affect the trajectory of the rocket. And so there's three ways that you can kind of do this in flight. And so the first one, which I'm going to go into more detail in the next slide, is just like having fins. That's kind of what the purpose of fins on a rocket is for. There's also an idea of like active fin control. So you can kind of see in the bottom right corner of the slide, these fins are able to adjust slightly depending on the conditions outside during the launch, which is able to maintain a certain stability. And then there's also this idea of thrust gimbaling. So if you kind of parse that phrase apart, thrust is what Dylan was just talking about with propulsion. So you have like stuff getting propelled at the back. And then gimbaling kind of refers to this like side-to-side motion. If you know, like a camera gimbal, it's kind of that idea. So it's basically about changing the direction of your thrust based on, again, conditions to achieve stable flight. And so you can see in the diagram on the bottom left side, like the little NASA thing, a really key idea with stability is that you need your center of gravity of your rocket or other object to be above the center of pressure. And so going into kind of what that's supposed to mean. So I think you guys know what the center of mass generally is. If you have an object and you're trying to balance it on your finger or on a surface or something, especially if you're doing it on your finger, you'll eventually find some kind of like sweet spot where the object balances out. And that is going to be your center of mass, because that's kind of where your mass is equally distributed around that object. If you know like torques, it all cancels out. Basically, the weight is all balanced. And so you have that point. And then the second point you're going to look at is your center of pressure. And so that's kind of the center of the area of your rocket. So regardless of sort of the masses of things, your center of pressure is going to be right there in the middle. And so those are two separate points, right? But to have stable flight, you need your center of mass to be a little bit higher than your center of pressure. And so there are a few ways that that is kind of achieved. So the one that's used a lot kind of in, at least in our club with rocketry, is if you add weight to your nose cone, so right in the tip of your rocket, you can move your center of mass up because it gets a little heavier. It's like top heavy, which is really nice. Another really important part of kind of balancing this all out is also having your center pressure closer to the bottom, right? And so having fins down there actually kind of helps because it increases like your surface area and stuff, but that also messes with your air resistance, which is called kind of drag with aerospace. And so having fins is really crucial to having like good stability, but you also kind of need to strike a balance where your rocket has sufficient stability, but it also doesn't have too much drag on it. So that's kind of a fun part of, well, I guess my job in the team, which is designing all of the outer components of the rocket.
Yeah, so we'll talk a little bit about the navigation and control of the rocket now. So as you saw in the video that was shown earlier, it's really important that the entire flight of the rocket is like goes as expected, just because there's a lot of key components within that trajectory that you might not actually see happening, but it is actually happening in the background. So with the first thing in navigation control, that usually starts with our engine startup. So we actually use an electric igniter instead of lighting a fuse. We use like a launch controller specifically and to start our motors because it's a lot more safer to do it that way. And as Rian mentioned before, the fins are a super important part in controlling the trajectory. So that also needs to be activated. Cameras, without the cameras, we wouldn't get that video that we had before. So it's really important that we have all those components connected together. And other things that we need to like control and keep track of like throughout the trajectory is like payload experiments, keeping in mind altitude of the rocket, like referring to how like basically how high up in the air it is. That's something that we need to monitor very carefully because we do a lot of our simulations basically like with expected like trajectories in mind, and the higher it goes, there's like a potential like drift. There are parachute deployments are also like really dependent on how high the rocket currently is in the air. So those are things that we definitely need to be keeping track throughout that flight. And yeah, with the parachutes, as I saw in the video, there are two parachutes that we use. The first one is the Drogue Parachute. So this is like a smaller parachute that we deploy at apogee. So an apogee refers to like the peak of the trajectory. So this is basically when the velocity is like close to zero. And we launched our first parachute basically to just slow down the rocket slightly. It's not going to like completely make the rocket safe to like plunge into the ground, but we have our first one at zero velocity basically because there's no other wind like affecting it. So it's a lot more easier to like launch one smaller one to gently slow it down. And at like a second point, as it descends, we launch our much bigger main parachute. So there's two parachutes in total, and both of them are deployed using a black powder charge. This is also an explosive. So sometimes there's a lot of like components of like the point of the parachute that can be really tricky. So it's important that the parachute launches out of the chute like safely and efficiently. Next slide, please. Yeah, so with the avionics, avionics refers to like the electrical components of our rocket. So because like a lot of the components or a lot of the action items that we need to do throughout the trajectory are very electrically based, we need to have a whole system that keeps everything like together. So yeah, some of the things that we have are our altimeter. This is just basically going to measure the current altitude of the rocket. You saw in the video how like the number of like height was like increasing as we saw the rocket go up. That's because we have altimeters inside our avionics bay, and that just keeps track of like how high it's going. GPS is really important because we need to be able to track where it's landing. Sometimes like due to wind conditions or other weather conditions, it might veer off a little further than expected. So our GPS is really important for keeping track of where it actually lands. Gyroscope, this is going just to be measuring angular velocity. Accelerometer, as the name implies, it's just measuring the acceleration of the rocket. Radios, that's important for communicating with other systems. And our magnetometer is just going to be measuring the magnetic field.
So we wanted to take a little break now to kind of ask or like receive any questions from you guys surrounding the technical side of things. If you guys have any questions about how like a rocket works or functions and like the different components or anything over just like what we covered so far. I can give you guys a couple minutes.
Okay, I have a question. Do the electronics ever stop working because of how fast the rocket's going or because of the effects of everything else?
Yeah. Oh, go ahead.
Okay. Either way, but you can follow up after Colin. But main idea is with a lot of these electronics, we before we launch our rocket, we know exactly kind of where the apogee is, how far it's going to go, the velocity, things like that. So with those like constraints kind of in mind, we choose radio signals that we that will work for that, and obviously accounting for some type of error and stuff like that. So we always have communication with our rocket. In terms of like ways that it can kind of be damaged or anything like that, we have a lot of backups in place. Actually, it's throughout our rocket we have a lot of backups happening, because obviously it's a very volatile situation. You don't know what's going to go wrong. So in the case of like short circuits, or in the case of like the frequency is not matching during certain connections and stuff like that, we have kind of like emergency fail-safe procedures for that as well. And it's also built into our boards. But yeah, Colin, would you like to add?
I was just gonna mention, yeah, like we have like I'm on the recovery team, and one thing that we just actually were working on was designing an avionics bay. Just basically the section of the rocket that contains a lot of electronics, and one thing that we have to design is like a sled that we can slide in and out of the rocket easily, and also make sure that all the electrical components are secured very safely. So one thing that we've been working on is like make sure that the design like accommodates all of the wiring. The wiring needs to be like secured. You know, things can't be like flying out all over the place because there is open space inside of the rocket, so things need to be secured like very, very carefully.
Also adding on to that, the rocket has a lot of like temperature constraints and stuff like that, because obviously we have an engine at the bottom that's going very, very, very hot, but also different altitude changes, different pressure changes that can also affect how electronics work and communicate. So we definitely that avionics bay that recovery works on building, it has to basically be like foolproof in most ways. Yeah.
How do you maximize like the space? How do you most efficiently use the space you have in the rocket?
Does someone else want to try answering this question?
I guess I would say that usually the airframe is one of the last things we actually design. It's definitely built into everything, but the engine itself is usually a first principle. That's one of the first things we're making. I'm decided on the avionics, decide on the payload. So basically form fitting the airframe around everything else rather than fitting everything else into the airframe. So it's pretty manageable to try to optimize everything because you're going to make everything as tight as you can reasonably make it to begin with.
There's also things like structural concerns and stuff like that that we have to take into account because there's so many components. And again, like Dylan said, that a lot of that comes last. So we make sure everything works separately and great, and then we put it together. Are there any other questions we can answer?
I think there's one in chat.
Oh, okay, let me pull that up. What do you need to sense magnetic fields for? About like that magnet, about the magnetometer. Does anyone want to try answering that?
Not super involved with that, but was that part of our Muon detector experiment?
Yeah, I think it was. It was part of our Muon Detector experiment. So basically, the reason that's there is because of something that's a payload. I don't know if we actually completely went over what a payload is, but you have your rocket, right? But it's cool to watch it go up and down. But something that's also kind of fun to do is run experiments while the rocket's within flight. And this gives us a lot of information about how certain components and things and work at like different altitudes, different speeds, and that kind of environment up there, right? That's not very easily accessible. So when we're looking at this magnetometer, that was part of one of our payload projects. That was a muon detector. So if you guys don't know, muons are basically subatomic particles that are like elementary particles. They're similar to electrons with like a similar charge. However, they have a much greater mass. So sorry, give me one second. I think my Siri's going off. Okay, but yeah, they have a much greater mass, and they are found in the atmosphere. So that's why we had a magnetometer in that sense.
One of the questions that we had on the doc was, how do you organize your team so that you can get things done in a timely fashion? And do you set your own deadlines?
Yeah, there are a lot of components to our team, especially with like leadership and organization. It's always like a challenge to kind of approach and stuff like that. Me and Dylan are actually pretty involved with the leadership side of things of our team. And obviously we're still trying to constantly improve our team and make it more efficient in that sense. But we have a lot of different projects running simultaneously on our team. So like different engines, different rockets, stuff like that, and different projects. So we have like basically our team is split into several subgroups in that sense. And there's a lot of kind of like layers of the leadership process. We have like obviously like a president. We have people that deal with more like the administrative side of things, people that lead more on the technical side of things. But obviously communication is the ground of everything. Dylan, do you have anything to add?
This is kind of definitely, as already said, it's kind of a layered system. We'll have the president, vice president at the top. We'll also have like systems lead, systems engineering kind of helps organize everything. We'll have outreach, we'll have business, different, as already said, we have some non-technical aspects that definitely help lead the team on that side. Then we will also have leads for different specialties, basically different areas of expertise. I'm propulsion. There's also airframe, avionics, recovery. I think there's a couple others that I'm blanking And then basically for every individual sub-project, we will have a project manager who kind of sees that week to week. And then just general members who are engineers on those projects. So it's kind of layered. Everyone has their own responsibilities, but it works. It's worked for us in the past.
Anything else we can answer?
Well, you guys talked briefly about this with the diagram of the pumps and the fuel. I was kind of just wondering how exactly the pumps work and how you prevent so much pressure from going backwards into the tanks and still letting the oxidizer flow out and the fuel.
Dylan's a pro at this. Do you want to go for it?
Yeah, so this feed system is heavily simplified. There are a lot of additional fittings involved with this. Two main ones that you kind of hit on that are present for, again, the reasons you pretty much said, is we have regulators for one, which helps regulate pressure down from a higher level to a lower level. And we also have check valves, which only allows flow in one direction. So if you put those together, you basically can get this high pressure, get it down to a lower, more manageable pressure, and check valve maintains it into one direction. As for how the pumps work, that depends on the specific implementation. I think a common one is the central fusion pump. For us personally, we do not use pumps. We use a pressure fed system, precisely because pumps have very high flow rates and we don't need that high flow rate. Pressure fed is enough. And by pressure fed, I mean we would have an additional tank that isn't here with some pressurizing agent for liquid engine 2. Again, that's the project I'm on. We're probably going to use helium. Nitrogen's another option, basically anything non-reactive. And it just essentially physically pushes the fuel and oxidizer where you want them to set a certain flow rate. Then you can get them down to the combustion chamber in the ratios you want them to, combust them, shoot the gas out the back, got the rocket.
Yeah, again, there are a lot of like fail-safe components as well, like relief valves and like servos that like handle things in case of emergencies.
Yeah. Also kind of touching back on avionics, we'll a lot of times have normally closed solenoid valves, which are electrically controlled valves, and normally closed means when it loses power, it'll shut. So that's another fail-safe, that if you lose control, it'll just close, system shuts down. Don't need to worry about anything else combusting.
I think that's all we have for questions right now. Do you
That's
guys want-
awesome. Cool. Moving on to like the next part, Dylan is going to lead this, but we have kind of a cool rocket simulator that we kind of wanted to walk through with you guys. And yeah, Dylan, do you want to take it away?
Yeah, so this is a link to a rocket simulator. It is relatively bare bones, just kind of gives you an idea for how we balance the different considerations for a certain goal. I will give a warning that this is not entirely realistic because it treats mass thrust and thrust time as like independent variables you can set on their own. They are extremely interconnected. So you really can't just set them completely anywhere you want. They're definitely related. But this does give you a chance to try to set things relative. You have a goal of getting to 400 kilometers. Can you get there? Obviously, you have a super high thrust with long burn time and no mass. You're going to miss it, accelerate past it, probably get some aerodynamic instabilities as well. But at the same time, if you have a high mass, low thrust, you're just going to sit on the ground. So these are all parameters that we do think about. Again, they are interconnected. Thrust time's kind of a interesting one because your time on itself isn't necessarily a good or a bad thing. It's just how long do you have that given thrust. So sometimes solid motors are traditionally very high thrust, short burn time. An advantage of liquid engines and why they're very common is you'll get moderate thrust for long burn times, which will give you more net altitude and more control. Yeah, so again, those are just dragging sliders. You can set those wherever you want, play around with them, see how they relate. Then the two other options, drag, kind of self-explanatory, just do you have air resistance? If you want this to be actually be realistic, that would obviously be yes, unless you're launching off the moon or something. Even then you'd have some, but less. And then mass change is basically when you're firing the rocket, your mass is not constant because you imagine that the fuel itself that you're actually burning is part of the mass. So as you're burning it off, your mass is actually going to decrease over time since you're actually expelling that off the vehicle. So that's another kind of consideration if you want to make it more realistic. But yeah, that's pretty much what we had. You can just mess around with this to see how things relate. But this could give you a baseline idea for things we'll consider, but this is relatively simple related to an actual rocket design. There are more
Yeah,
advanced
so-
simulations if you're interested in those, but
Yeah, so here's the tiny URL for the simulator, and we wanted to give you guys about 10 minutes to walk through the simulator and try and achieve the highest altitude that you can. So by playing around with the variables, and we were going to ask that if you guys want to work in groups, that's totally fine too. But yeah, just play around with the variables, see kind of yourself how these variables relate to each other, how that kind of relates to a lot of the theory that we mentioned before. With the default setting right now on this web page, if I do click launch, you will see that, give it a second, it will fail. Yeah, so this is a partial launch, and you can see a lot of these components are really, really slow, or are like really, really off compared to what we want it to do. So yeah, kind of play around with it. What kind of ranges are we looking at for a lot of the components and stuff like that? Yeah, so we'll give you guys about 10 minutes if that's good. We'll give you guys about 5 more minutes to wrap up, if that's cool.
I think some people got it. I ended up with a simulation that just keeps going.
Oh, awesome. But yeah, I'll try to get as high as you can with the simulation. But yeah. Just kind of checking in to see if most people are done. And yeah, just wanted to hear from you guys. What worked, what didn't, what kind of like parameters did you guys play with the most? What affected the rocket's flight the most, or what didn't affect it as much?
Well, I noticed that like maximum thrust and maximum thrust time with like the minimum mass possible
Yeah, and why does that kind of make sense?
Because like it goes faster if there's less mass.
Yeah, Newton's second law, basically. If there's more force, less mass, acceleration is greater, right? F equals ma. Any other kind of main takeaways from this?
I noticed that if you put the thrust up all the way and the thrust time up all the way and you made the mass very low, then it exploded.
Yeah, and kind of why do you guys think that would happen in that sense? Like the extremes.
In that case, it would be structural failure because it's going too fast.
Yeah, and also thinking about what kind of mass there is, like a small amount of mass just can't handle that type of combustion in the first place, right? There are very few materials that are that highly combustible, if at all. And yeah, you guys basically got to the point. Any other kind of takeaways?
I noticed that if you wanted to have a certain amount of fuel in your rocket, your mass would have to be a certain amount. Like if the mass was changing, like it wouldn't let you go below a certain mass with the given amount of fuel because it needed to carry that fuel. And
Yeah, exactly. So there are a lot of, even in this extremely simplified model of rocket flight, we still have these mass constraints, right? Especially on the fuel side of things. And fuel is extremely heavy when we're looking at our overall mass percentage of our rocket. Fuel and oxidizer takes up a huge portion of that because that's kind of what makes our rocket go up. So yeah. Anything else to add? Okay, cool. If not, we can move on to the next part, which is a little bit of like the college and career questions you guys sent our way. And this is gonna kind of be like an open discussion between Colin, Dylan, and Ria, if you guys want to kind of jump in and answer these questions about like careers related to rocket science. And these like two smaller bullet points up here. If you guys want to hop in.
Yeah, sure. I can maybe start with the first one. I think I'm currently actually a third year student, so I've already spent 2 years at UC Berkeley, and I only joined STAR this semester, and this is my first time getting involved in something aerospace related at UC Berkeley. I haven't had hands like I've had 2 years of engineering experience, but I haven't had anything like really hands-on in that field. And honestly, it was a little intimidating to me at first, but I think especially like learning in a setting in like a club like this where I'm learning alongside my peers, it's been pretty easy. Like the content itself isn't easy, but it hasn't been like stressful or difficult to say. Um Especially like being part of like a smaller sub team, I'm really getting exposed like in like a small amount. Like I'm on the recovery team, so although I don't know too much about like the other sub teams so far, I do feel like I'm getting like good experience in one area, and hopefully I can slowly branch out and learn more.
Yeah, kind of going off of that into like the career settings. A lot of there are a lot of careers in rocket science, and also rocketry is an extremely complicated field. It's not all like building rockets necessarily. There are a lot of other side components that some of us like mentioned over. A huge part is the software and electronic sides of things, right? And another huge part is things like administration. There's a lot of business to the rocketry field, and also in general, the whole field of space exploration is an extremely huge field, and rockets are only like a very, very small percentage of that. And within the field, there's a lot of diverse opportunities and resources and things you can get involved in. And being on a rocketry team can help you with your career. A lot of alumni from our club go on to work at amazing companies like Google, Apple, and they also take like the rocketry side of things like SpaceX, Boeing, Raytheon, that kind of side as well. There's a lot of research oriented parts of rocketry as well. It's an extremely complicated field, and there's a place for everyone. No matter kind of what you're really into, it can be tied in. So yeah, do you guys, Dylan and Ria, have anything to add?
Not too much. Just that again, it is a huge field. I know when I was getting kind of started with it, and I think a lot of people getting started with it, you see the rockets, they're very visible. But ultimately, the reason rockets exist is so you can put other stuff in space. They serve a function. It's not all about just the rockets themselves. So if you're interested in the field, there's a ton of other opportunities to work on satellites, microgravity pharmaceuticals, different manufacturing things. I know asteroid mining is like going to be the next big thing that's supposed to make the first trillionaire if someone figures it out. There's a huge space debris issue if you want to try to address that. There's really just a ton of things that aren't strictly rockets. And if you are interested in rockets, then by all means, there's SpaceX, Blue Origin, Relativity. There's a lot of rocketry companies as well. So it's definitely a big field. It's a growing field. I think it's obviously we're biased here because we're on the rocketry team, but I think it's a very good field to be getting into because the jobs are increasing more than the supply of new graduates, and there's just a lot of stuff to do, and you're pretty much on a daily basis, your job would be to go build stuff for space, which to me seems like a good way to spend a career.
Yeah, I think since Arby brought up kind of like people, our alumni going on to like work in all these different industries, just like I think I mentioned this at the beginning, but I am actually a freshman at Berkeley. And so I'm kind of like starting all of my engineering coursework. And that means I'm also new to STAR. And what I kind of realized when I got to school was like, I am really interested in aerospace, but you don't get a lot of hands-on experience, like Colin said, in your first couple of years, especially, but even throughout all 4 years, because you spend so much time in a classroom. But I think what's been really awesome about STAR is even in the first just couple months of the year, I've already gotten so much hands-on experience and mentorship and learning aerospace and rocketry. And I get to use all these different softwares that are not taught in a classroom setting here. And I get to get all this practical knowledge, which in reality is going to probably be more useful if I get an internship or a job in basically like this kind of career field, as opposed to like all the little nitty gritty bits of like multivariable calculus that I'm studying as well. So I think that's been like a really, really awesome part about joining this team. And I know that if I came back and like spoke to you guys in 3 more years, I'd probably say the exact same thing where regardless of what you're interested in, if you're able to find like a club or an organization that gives you that kind of practical experience, that's always going to help you with your career, no matter what you're trying to do.
Yeah, great points, everyone. Did that kind of answer this question? Do you guys have more specific questions regarding rocketry careers and space exploration in general? Cool. We can move on to the next questions. We had a couple specific questions about rockets that you guys sent our way. And I think we kind of answered some of these throughout our presentation. However, some of them we didn't. Colin, you haven't spoken a little recently. Do you want to try and address some of these?
Yeah, so with the main components of rockets, so I'm not too familiar with the other big components, but at least with I know that like with all the different components, such as like the airframe itself, like the engines and avionics bay across the different teams, each sub team kind of like works on their own like kind of project, but a lot of the teams will have to like in the end it's one giant rocket, so a lot of the different teams will like reconvene and assemble the rocket and present like their specific work. At least for me, I'm mainly working on state separation as well as like the avionics bay. So that's only like 2 of the components of the rocket. But that's something that's like really integral to the entire like trajectory, and every single piece of the rocket is pretty important to the entire launch.
Going off of the last bullet point here, how many experiments do you have before big competitions? So yeah, this is going off of a really key point here. We want to definitely test all our materials and things that are going into the rocket before obviously we launch. So a lot of the components that we're putting into the rocket, we test multiple times beforehand separately. And then we also test them like 1 or 2 times together, right? Depending on how like interconnected they are, stuff like that. Each and every component is very extensively looked at and very thoroughly kind of judged to see whether it's good enough to go in, or like if we need a replacement last minute, stuff like that. We are definitely very meticulous about kind of how we're testing everything before launch and stuff like that. We have pages and pages of procedures. Yeah, it's a very complicated process, but very, very fun. Do we have any other questions that kind of surround this topic?
I have a question. What are like your favorite parts of being on the rocket team?
Do some of you want to go first and we can circle around?
Yeah, for one, I think it's just great community on campus. You get a whole bunch of aerospace people. Thankfully for you guys' time, you will have an aerospace major on campus. None of us here have had that. So it's nice kind of having an aerospace community outside of formal coursework, mainly because it doesn't exist. To actually, as I kind of touched on earlier, get experience with this, give you career prospects. We didn't mention before, we also host a ton of educational workshops and host outside speakers come in, some companies, recruiting events, stuff like that. That's why we have pretty good placement at these big companies. So it's just nice having that kind of community in there, as well as you're building rockets. I mean, why wouldn't you want to build rockets?
Yeah, piggybacking off of what Dylan said, the people here are really just amazing people. You just kind of like get to hang out with your friends and like tinker and build rockets, and it's really, really fun. And I've met like the coolest people on the team that have helped me with everything. And to be honest, STAR is like a really big family. We have, even though we build rockets, we also have like we have a Discord, and like we have a lot of like cool fun channels on our Discord as well. Like we meet up to have dinner, we hang out, like it's basically like a nice little family in college. So wherever you guys end up going, I highly encourage you to join a teamer of some sort. Do Rhea and Colin want to add?
Yeah, sure. I'll add on to that. I would definitely have the second or third of what you guys just said there. I think one thing that's really important about like STEM in college, especially like if you come from a background where like you weren't really exposed to that like in high school or something, is having a community of people that you can learn with. Especially for me, I didn't really feel like connected to like the engineering community at all for my first 2 years. Like I wasn't like I took classes with the people in my classes, but I wouldn't really like go beyond outside of that. And since being in STAR, I've like definitely met a lot of people that I can like talk outside of class with about like the same things that I'm interested in, and also just like things that were not like didn't really know any like I didn't really have any engineering friends until I joined the STAR, not gonna lie. And so that's really one thing that's been nice, just to like have a community of people that I can like go through this experience with, because like engineering or STEM in general at any college is like pretty difficult. So going through it with people that like you can like rely on is like pretty nice.
Yeah, I think my answer is pretty much the same as Colin's. I didn't have a lot of engineering friends before I joined STAR either, and still like all of my engineering friends are pretty much from STAR. But I think what's really nice is that Dylan mentioned that we don't actually have like a formal aerospace major yet, but even when it comes around, it's kind of like a small niche part of engineering. And so it's really nice to be able to find a whole bunch of people that really love that same like very specific field. Even though everyone's from very different majors, it's kind of like we all have this shared interest and we all want to like build rockets and just kind of have fun. It's really nice. But another really nice part about STAR is that because like I'm a freshman, right? But there's a lot of people in the club who are like sophomores or juniors or seniors or alumni who are still super connected. And so you kind of have like this, you get a lot of mentorship out of the program, both from like a technical sense, as in they help you learn about rocketry and building rockets, but then also just kind of in general. Like I was supposed to have a meeting with one of the juniors, like leadership members in STAR, and it was supposed to be like a half an hour design review to talk about like a rocket I was working on. We ended up sitting in a cafe for 2 hours, and we only had a design review for half an hour, but it was really nice just to get to talk to somebody who's in the same major as me and the same interests about like classes and life at Berkeley and finding like different support systems and communities and things that we have in common. And so it's just really nice to get to meet people who are like friends, but then also mentors. And then I guess like in the flip way, get to find people that you're able to mentor as well and get to know. So it's just like, it's a really nice community in STAR.
Yeah, that's awesome. Thanks guys for sharing. But hopefully that gave you guys a little bit more about how much we love rockets and we love our team. Yeah. Some of the other questions we had, how much time do you guys spend on each phase of creating a rocket? So a lot of the time we do work on deadlines because we are working towards a competition, but we basically have a whole year to assemble everything. But obviously we're trying to get things done a little early and stuff like that. And there are breaks and things like that. But yeah, I know as far as like a lot of these types of design processes and manufacturing processes go is we have a lot of design reviews. So this is like a concept that we borrowed from industry and how industry operates in general. But basically before we actually make anything or before we actually go forward, we want to consult everybody that is knowledgeable in the field and can help us out, give us advice. So we have like a bunch of weird acronyms for all the types of reviews, but design reviews in general. But yeah, we basically quadruple check every single decision that's made, and that does take time and often takes months on end. But I can't speak to a lot of the others, but other sub teams, but I know that a lot of things are very interconnected. So some tasks have to get done first and some tasks get done later. But yeah, basically every decision is vetted by as many people as possible. We also call in alumni, we call in other rocketry teams to help us just for advice and stuff like that. And we also call in industry professionals to kind of give us advice on our design. So if they could see something that we don't necessarily see, and as in like flaws or like failure mechanisms that could happen with our rocket. But yeah, the aerospace community in general is very, very awesome. And we communicate a lot with industry professionals and other college teams as well, who we're competing against, which is kind of nice that we still have that kind of sportsmanship. Anyone want to add? Cool. Well, that's kind of about it for what we had prepared. I hope you guys learned a little bit more about rockets and are a little bit more interested about our community here at UC Berkeley STAR. I will be leaving my email in the Zoom chat, or I think you guys have my email, but like feel free to email me if you guys have any questions later on, if you guys are interested in applying to universities for aerospace engineering or physics or any of that, or I'm sure some of the other STAR members here would love to chat with you guys as well if you guys are looking for mentorship. And yeah, do you guys have any other questions, comments, concerns, anything I can kind of get back to you on?
Oh, okay. I have one last question. Is there any way we as high schoolers can like participate on the STAR Rocketry team in any way?
Yeah, we can get back to you about that, but you can definitely probably attend some of our design reviews, kind of see how this process works. You can definitely probably like tag along to some of our meetings, see exactly like what it looks like, what it's like to be right there in the moment building rockets, and maybe even we'll definitely keep you guys updated about any types of build days or launch days, to see if you guys can like either live stream in or something like that. But yeah, we'd love to have you guys kind of involved on the team in terms of like, if you guys just kind of want to see what the environment's like, how it works, and who knows, you guys could be could give us a tip or two as well, right?
I think we're out of questions.
Yeah,
Thank you so, so much for speaking with us today. This was fantastic.
I learned so much. Thank you.
Awesome. I'm very glad to hear that this was a really nice, I guess, like productive session. And it was really nice meeting you guys all, meeting all of you guys. And I hope you guys all learned something awesome about rockets and kind of want to go out there and build some rockets. So yeah, again, feel free to contact us. I can send you guys their emails if they're comfortable, to your email, Alessandra, if comfortable. And yeah, feel free to reach out anytime, even if you guys have like other projects you guys are working on and want like some kind of like college students to review anything, or if you guys want to get involved as well, feel free to reach out. But yeah, this was great, and yeah, really nice meeting you all, and I hope you guys have an amazing rest of your week.
You
Thank
too.
you. You too.
Bye guys.
Bye.